Welcome to Complexity Made Simple. And in this video newsletter, well, we're going to have a look at a case study which is all about measurement system error, MSA, measurement system error, but not using the traditional technique. It's about spotting measurement error using the run chart. So this is all about, it's the power of the run chart. One of the things I always encourage my clients to do with every problem they have, plot the graph. Never look at the numbers, because the run chart, and I realize this by talking to lots of my clients, the run chart has diagnosed for me so many different issues over and above just there's a trend of some kind. Yeah, there's patterns on run charts that tell you different things. And in this case, it's going to diagnose a measurement problem. And I've seen this pattern a few times on run charts. When it's there, it's clean and clear. And the minute you see it, you can't unsee it. And it's such a great little technique. You can diagnose problems over and above. I've got a machine that doesn't work. You can immediately see a measurement problem. Maybe then conduct an MSA to diagnose the full scale of the problem. But we're going to take a look at a case study. The run chart is going to show that we have a measurement problem. Let's take a look.
Okay, let's take a look at this latest case study. And in fact, this is a case study that has only just started. It's not a complete project, but something's come up in the case study. There's a little pattern that's turned up on the run chart. That's just a great little learning point. It's a pattern that you often see in data, and it's just a great opportunity to learn how to read your run charts and to see patterns that are important to you. Now, this is the project. Look, it's a carriage. It's a carriage plate. So what we're looking at is the frame at the back rather than the bearings that have been assembled onto it, and they have a problem with a particular tolerance, a particular dimension. Now, just before we go in and look at the run chart, just something to say about the problem statement. It would be great if the problem statement was much better. High variation in the magnet dimension. It would be much better if they said what the defect rate was. It would be much better if they quantified the variability in the magnet dimension. But that's just a small point as we go in and look at the run chart. So let's take a look at the run chart. Now, they've measured 180 pieces. And this run chart's come up. Now, I haven't put the tolerances on here yet. I'll do that for you in a second. But before we do that, just something to say about this. Your processes are supposed to be random number generators. So whenever you look at a run chart, you should be asking yourself a question. Is this a random number generator? Especially if what you're measuring is a completely continuous scale. So the ability to be anywhere on a particular scale. Now, we happen to be measuring in millimeters, and the way the graph is put together, look, it's moving in 0.02 of a millimeter. But what you are seeing the data move in these lumpy steps. So the data can only go on part of the scale. There's no ability for it to subdivide and to be anywhere other than on those lumpy sections that we've seen. So look, the data is sitting in lines. Look, there's a line of data there. There's a line of data there. Look, there's a line of data there. There's a couple of things that this often tells you. When you see data coming at you like this, in these lumps, these lines like this, either there is not enough decimal places. So it could be that what we have here, this is about decimal places on the measurement equipment. Now, this is the case in this case. It could also be sometimes something that the operator is doing. This especially happens when you have a tolerance limit and the operator has lots of results below the tolerance limit. He doesn't want to record bad news. So what he does is he puts each one dead on the limit. When you see results dead on bottom tolerance, or indeed the equivalent, especially on the same chart, results that are up there as well, dead on top tolerance, that's a sign something's wrong. The operator's doing that. But in this case, the way this data is moving in large jumps, it's because of the decimal place problem. So let's put some tolerances on this thing now, and it shows you the scale of the issue that this is going to cause. Clearly we've got a problem because we've got lots of variability. So we have a problem that we've got this natural variability here. This is how big it is. It's not going to fit inside the tolerances, whatever we do at the moment. But even if we removed that variability and we tried to get the results to fit inside the tolerance, we have a problem with our current measurement system, because the current measurement system will only allow you to be in three places: top limit, mid, or bottom limit. It doesn't allow you to be on a scale inside those two red lines. So before we do any work to sort out the variability, they need to sort that out. They need an extra decimal place on their measurement system. Now you can see that just from the run chart. This is a common pattern. It does appear quite often in projects. It especially appears when these days I'm dealing with companies that tend to be making high specification parts, and although they're trying to machine things to a high specification, they actually can't measure it to the specification they've been asked to achieve. So you see this quite often these days. So it's a pattern that you're going to see. Now the lads that are doing this project have also done an MSA, and the MSA agrees with this particular problem. So let me show you how the MSA agrees with the results. So if we go down, just scoot to the measurement system result. The resolution, it says the resolution is at 3. What does that mean? Well, it means this. If they tried to draw a histogram, they would only be able to see 3 columns on the histogram like that. It's not enough columns to see the distribution properly. The minimum this needs to be is 5, because with 5 columns you begin to see the distribution appear. So this thing here, which should be at a minimum of 5, is agreeing with the pattern that we're seeing on the run chart. Now, there's work to be done. They've got to sort out the measurement system. They've got to sort out the variability in the process. It's a relatively straightforward thing to fix, to be quite honest, and I'm sure the lads will fix it quite quickly. But they've got to sort the measurement system out first. But it was just a great opportunity to show you a pattern that appears on a run chart quite a lot, and it's telling you something instantly. It's also a point that, of course, you wouldn't see that in the data. So if you just looked at the data set, it's unlikely you would see that. In fact, it's impossible that you would see that pattern just by looking at the data. So it's making another great point that you really should put data onto run charts, put data into other pictures, draw pictures with the data, see the patterns, and then you'll learn something about your process very, very quickly, and then you can put it right. Draw patterns, learn something about your process.
Okay, well, there was the case study. It's very simple. The pattern was very simple. One of the things I would say, as you go through your journey becoming a world-class technical problem solver, if you plot the run chart always and every time, the more you do it, the more you will see things on charts, and you'll begin to realize how fundamentally powerful they are. They are such a simple diagram, but because they're such a simple diagram, people don't want to use them because they think they'll see the pattern in the data. The pattern that you just saw there, you would never see that in the numbers. You cannot observe that in an Excel spreadsheet. So my advice, guys, plot the run chart first, last, always. You'll see patterns that, guess what? You'll use them to make more money.